Well, it's official, folks. We are now in week 9. So congratulations on surviving midterm week. I understand probably some of us are still in recovery mode. We have a class of 4 people, but we're still going to make it happen today. Hopefully we get more as time goes on. But for the wrap up of what's going on with the announcements so far, we're nearly done in section 3.6. We're working our way through example 2, halfway through that problem. And the third example is the final one of those set of notes. Then we'll turn over to section 3.7, and this is going to be our last set of new differentiation formulas. So we're nearly there. Here in 3.7, we're mainly going to be looking into taking derivatives of logarithmic functions. So we're also going to use this document extensively on properties of logarithms to use them along the way. So it's kind of a dual duty section. We're doing calculus derivatives at the same time reviewing information about logarithms, which is a very good idea because those get kind of foggy after some time using them. But we're probably going to finish this potentially maybe on Thursday, but more likely when we return next week on Thursday directly after the exam too. So that's our larger announcement. We have our second exam information all filled out. The second exam is going to be held officially on Tuesday. And this is always a little bit confusing because there's the in-person section, the Pocatello section, and as far as it goes for the online Pocatello section, we won't have class at all on Tuesday. So even if you schedule your exam to be like at 4 o'clock or 8 a.m., something like that, which you're allowed to do, logging in for the Zoom meeting on Tuesday is not going to have anything but an empty Zoom room. That's always a little confusing. But for the people in the online section, I should have sent you an email detailing the next steps to contact the testing center. And if you didn't get an email whatsoever, my assumption is you're taking the exam in the classroom. Any questions at all so far, folks, about the exam or knowing where to be? Okay, and let's keep on scrolling down on these. The other bit of information is all of this stuff. This is basically just kind of a redo of exactly what we did on exam 1. And we'll keep this pattern going when we get to the next set. So at the end of this week here, we'll know exactly what's on exam 3. All the information gets filled out. We go to, say, the end of this week right here, we'll have a kind of a breather review week. And then I'll be at the end of the third exam week, also filling out this information. Essentially, it's going to be a really busy last 3 weeks, but that's how it goes every semester, and we'll definitely get through it. So just for a reminder, a rundown of what all this information is, best way to study for exam 2 is get caught up on these sections. So make sure you're caught up on your quizzes, make sure you're caught up on these sections in WebAssign. And as you're getting caught up on those sections, have this available in front of you. Either have it available on screen, maybe you'll print it out. Just keep in mind, though, that this is on the real second exam, so you don't have to bring it to you on the exam setting. But having this available in front of you will inform you what are the formulas that you're allowed to actually have in the exam setting. These are the things that will be provided. And it's also going to inform you on what formulas do you need to have memorized. So anything on here, make note cards out of that kind of thing as a test taking strategy. So that's going to be the last page of the real exam. This is just a redo of the allowed calculators. Essentially, we're excluding the graphing calculators like the T84. If you have a basic scientific calculator like either one of these, it'll work out just fine in the exam room. And last thing to discuss are the sample exams. 3 different versions like before, so that's a little bit confusing as well. But here's the idea with all these versions. On the first version, this is just textbook exercises. So you can go to WebAssign on the digital book, go to the section, and then just try out some of these odd problems. It's a long list of problems. So the idea with this document is you want to go to the area you feel like it's the biggest struggle, where things feel a little bit more vague, a little bit more difficult. Maybe you're targeting chain rule problems, maybe quotient rule, product rule, that kind of stuff. Second document is the actual lecture notes that we did ourselves. I've taken out all extraneous information, so there's no formulas inside here. There's just problems, asking about what kind of discontinuities. This is my way to say it's a great candidate for an exam question. Comes up again as here. Here, another question could be writing out information based off continuity. And last potential problems would be doing limits like these. So these are the actual lecture notes. That means when you go through these, there's no solutions, there's not a lot of information. But if, for example, this is a confusing problem and you want to try it out, then just go up to the actual lecture notes here, and the solutions are all provided, and a lot of analysis on how we did it. You can see the video for a little bit more step-by-step structure as well. So these are the blank lecture notes. And finally, the last document, version 3, these are like the more challenging problems. They're a lot more hard, I'd say. Some of the problems are going to be a little bit more involved doing these limits. Some of the derivatives are a little bit harder as well. But the idea is not me saying I'm going to ask the hardest questions on the real exam 2. This is just a document for extra, more thorough practice. It's not an assumption that you're going to do every single problem here. More, you might target specific sections again, like 3.3, 3.4, 3.5, and so on. So come here if you want just extra, more challenging problems. Solutions are at the end of this document. Solutions here are this one in the actual textbook itself. And the solutions to these are just on the Moodle website. And again, we'll redo this exact same process when we get to exam 3 and the final exam. Maybe not giving as much detail next time, but any questions at the moment, folks, about the exam? Okay, well, we're aware the exam is on the table. It's also been sent to the Pocatello Testing Center. So when you get a chance, if you're in the online section, give them a call to schedule your exam. It's officially on Tuesday, but the reality with the Pocatello Testing Center is they have to work with your schedule and their own schedule as well. So if you need to arrange it for a different time on Tuesday outside the normal class time, that's totally reasonable and acceptable. And let me see here. Other things I want to talk about in exam 2 are more for when we come back on Thursday. I want to give a little bit more advice on what topics to expect here, study strategies, things like that. So we'll start off discussing that on Thursday. And additionally on Thursday, if you have any additional questions after our short discussion on exam 2, don't hesitate to ask. I'm happy to go over any kind of problem, whether they're from the documents here, problems from WebAssign, or just generic overall questions you might have. Even if there's a lot of questions, I think spending time on it would be well worth it. So that's my whole set of announcements. That was an 8-minute set of announcements. Any questions or comments at the moment? Okay, well, we're week 9 out of 15 instructional weeks and a final week. It's a pretty pivotal week because we're going into the exam week, and then we'll take a break. So let's get through these last problems here, and we'll be on a good shape for getting through the second exam as well. Well, this is just where we left off last class. This was a week ago, so last Tuesday. We're looking into exponential growth and exponential decay. But for exponential decay, occasionally we use the half-life formula indicated here. The half-life formula tells us that something is decaying exponentially, and if they happen to tell us the half-life of the decay, the amount of time for which half of your material has disintegrated, then it can be re-expressed in this way. Lambda depends on your decay rate k. But you could also solve for k, and in this formula right here, we were directly able to use the given half-life. We just plugged it in. Numerator is negative natural log 2. And really in just one go, we threw in our initial mass right here into that spot in the model. We threw in our k value right here into that spot in the model. And we got this right away. So a pretty rapid approach compared to, say, example 1, or example 2 rather. After we got out that information, part B was just taking the function we provided, throwing in 100,000 years, and just cranking out a value. But part C is a little bit different. This always deserves a little bit of extra description. What's going on in part C is there's an underlying formula. And the formula goes like this. If dm dt equals km, let's actually say this slightly different. Let's write it out this way. Here's the differential equation. And it implies the solution to this whole thing is m of t equals m of 0 e to the kt. That was this model that we're building out here, plugging in information step by step. But it goes backwards. If you take this and you are being asked a question about the derivative, all you want to do is go directly to this. It's a weird problem where the model itself has a specified derivative. And so when they were asking, after 100,000 years, at what rate is the sample decaying? All we did was we used this formula. We plugged in 100,000 years. Well, that computation is already done for us. So we grabbed the value, 56.4 grams, and just threw it into that spot. And this is K being re-expanded from above. So it gave us that value, and that's doing it as fast as possible. Reason we're making such a big deal out of this is a common follow-up question, because I mean, this is a calculus class, right? And this is the calculus in the problem, so we really can't skip it. But it's also the worst and most confusing part of the problem, because ordinarily, if a derivative comes up, your training is to differentiate that, plug in a value, but you're working excessively hard because the derivative is known. That's the big takeaway whenever a question like this comes up. Well, again, that's all stuff we did last time. We carefully cranked this out, got negative 0.0016 grams. So 100,000 years into getting the sample of plutonium, forget what it was, 239, the bad stuff, we're down to a decay rate of 16 tens, hundreds, thousands, 10 thousandths of a gram per year. Well, the question we're going to address is, well, how much time is it going to take for our original sample to just be 1 gram remaining? Well, any last questions, folks, with what we did before we finish off this one? Okay, really, first thing you want to do with a question like this is just turn it into an equation. It says how much time will pass, so we're talking about time t, for there just to be 1 gram remaining of the sample. We're talking about mass at time t when they mention grams then, and we want it to be exactly just 1 gram. So this entire sentence here can just be re-expressed as this. We're solving for time t here, and we'll round to the nearest tenth. And that just means we want to go up to this spot here, import the model down into the equation, and let's use color coding just to make that a little bit more specific. We're going to take 1,000 e to the power negative, I guess I put that in blue because that's part of the decay rate, K, t natural log 2, divide by 24,110 equals 1 gram. So just one big substitution for mass at time t. That's the left-hand side. We imported the entire right-hand side, dropping into that equation down below. That's the key step, and then now it's just all algebra from here. Well, I guess that was an algebraic step, but any questions so far? Okay, now that we're down here, let's hide that problem just for a moment. See if we can get some extra space going. There we go. Next steps are isolate the exponential function, the base E exponential. That means we should just divide both sides by 1,000 right away, and we get e power negative t natural log 2 divided by 24,110 equals 0.001, so 1,000. Next step, we take the natural log of both sides. So natural log e negative t, natural log 2 divided by 24,110. Here's where you could skip a step if you feel very confident on properties of logarithms right here. I'm writing in this step, even though it's kind of a lot of writing, just to show in plain math language, I guess I wanted to say, what that step looks like if you come back to these notes. But the punchline is that's just gone immediately. Let's use this little mathematical notation of follow the arrows so we don't have to go to a next page. Copy in the left-hand side. I'm going to write this in as negative natural log 2 over 24,110 times t. So I'm moving t around just for clarity of reading this all out. I wanted t to be in this spot just so I'm not accidentally saying t minus something when it's really multiplying. I put it in this spot because now we're equation solving. It's just easier to see the coefficient in front of t rather to put it on this side. That would be kind of unnatural. Right-hand side is natural log 0.001. And now we do the division step. Dividing by the fraction here just means multiply by its reciprocal. So t would then be equal to negative 24,110 over natural log 2. So that's the reciprocal part. Multiplying the right-hand side, natural log 0.001. And if you're looking at this with a very critical eye and you're deciding to yourself, this isn't right. That's a time variable and the right-hand side is negative. Good on you. You're thinking about the context all along. But this is where logarithms are pretty tricky. Let me put a bracket here as opposed to a multiplication, just to show that right there. This looks like a negative number, but actually it's positive. Let's take another look at the logarithm while we're at this. I forgot to open this to start off class, so this is like a small mental break for us. Now finally, let's put in y equals natural log x. This could have been any logarithm, but notice what it does. Any logarithm whatsoever always goes through this point exactly. If I can click on it, there we go, right at 1, 0. So that means if you plug in a number that's less than 1, you're on this end of the logarithm and your output is some negative value. Looks like a large negative value. Natural log 0.001, I guess not that large, but it is about -7. Really weird, right? It's easy to kind of miscommunicate what's going on with the algebra, even as you're doing this, making no mistakes. Last step, throw it all into the calculator. Let me know if you're getting a different value, and we'll look at it more closely. In the calculator, I would go -24, 110. There we go. Make sure you get the right number of digits, natural log 2. Ordinarily, I put it in like this, just being hyper careful on the calculator. Multiply it by natural log 0.001. And this is the amount of time in years. 240,275.1 years. How much mass did we start with? Let's see if that feels reasonable. We started with 1,000 grams. Half-life is every 24,000 years. So to get to 1,000th of this, 100 half-lives had to occur. That's just this multiplied by 100. And that looks like it's very close to being accurate. So we're in the right ballpark of this. And we can now say t is approximately, I forgot the digit already, it is 240,275.1 years to get just that amount of mass left over. So by that time, there's still a concerning amount of a dangerous radioactive isotope, but we are all long gone by that point. Our dust has turned to dust at that point. But any questions at all, folks, on the conclusion here? Okay, well, this is the half-life in a nutshell kind of a problem. I felt like we shouldn't just leave it there. We got through this problem in a really nice way because the half-life formula provides directly a formula for the decay rate. So any problem that just directly tells you a half-life is a pretty fast question, like what we saw here. We just get K right away, import the information, and run through the problem. So what happens when the problem looks like this? We don't do a question like this. We're not really doing exponential decay in a fair way because we need to cover this kind of situation as well. It's kind of like a hypothetical. It says, if we're thinking in terms of a hypothetical, suppose you somehow had tritium-3. I believe this is used in like medical radiological sciences. Correct me if I'm wrong on that. I'm not completely sure on these things. But suppose you have a sample of tritium-3. And in 1 year of holding onto that sample, you only have 94.5% of it remaining. Question you'd want to answer to yourself right away, well then, what was the half-life? It could have been any kind of isotope, and you want to verify what's the half-life after making the measurement after a certain amount of time. Because we're talking about, well, sample decay to 95% of its original amount after a year, this doesn't alone tell us we're dealing with exponential decay. But when this word comes up, it absolutely does. Half-life only is occurring in the context of an exponential decay model. So from that word alone, it tells us we're dealing with, once again, mass at time t equals the initial mass at time 0, times e to the power kt. The actual question we want to answer, though, is what is lambda? So let's just put this here, just as a reminder. This is the overall thing we want to resolve. And now, somehow, some way, we have to use the fact that we have a model right here, some of this initial information, to get a value of lambda. Notice what's missing. Nowhere did this problem even tell us what the initial mass was. We have no clue. Although we know is m of 0 is greater than 0. Measured in grams, kilograms, we're not sure on the unit either. We just know we have an initial mass, it's some positive quantity. We don't know its specific amount. Other information we do know is this right here. This is basically the only given information about the problem, right? Everything else was the context of the isotope we're handling. So this says, well, mass. It says after a year right here. So let's put in mass at time 1 year is 94.5%. So 0.945 of its original amount. But when they talk about the original amount, that's the mass at time 0 once again. So this is a pretty strange kind of problem because now we have this equation telling us in 1 year, 94.5% or just 0.945 times m naught is the only piece of information we have now. But that's something we can work with. Any questions at all, folks, with the rundown of all this given information so far? Okay, now that we have all this information, here's the next thing we can do. This condition here, it's not the initial condition because we don't know initial mass whatsoever, kind of frustrating, but it is a condition. And it's a condition when the time is exactly 1 year. So we can work with that. Mass at time 1, plug 1 year in here for time, and here's our first big substitution. We get mass at time 0, e to the power of k times 1 now in place of the time variable t, equals 0.945 mass at time 0. So now in this equation, we're not dividing by 0 when we cancel mass at time 0. That's kind of interesting in a way, right? This equation right here, or this sentence right here, provided an equation that already involves mass at time 0, m naught. Then when we made the substitution on the left-hand side, because mass at 0 comes up again in the model, here it is, and now we just divide by it. Mass at 0 divide by mass at 0, both sides of the equation. Again, without this justification, we could be dead in the water, but the problem makes no sense if the mass is 0 initially. Nothing's changing at that point. So this is a natural assumption in the problem. Do a big cancellation like this, and we get that e to the power of k is 0.945. So example 4 doesn't tell us what m at 0 is, and when we really go through this problem, we start to realize it actually doesn't matter. We can go through, actually find the half-life, and it didn't even have any influence on what the mass was initially, other than it just has to be positive. Strange problem, right? But now back at this step, our goal is to get the half-life, but now we're solving for k. Take the natural log of both sides. On the left-hand side, this is the cancellation we expect through properties of logarithms. And that means we've done it. We've solved for k. Well, we haven't done it. We still need lambda. But to get lambda, we do need k, so we're on our way. K is the natural log of 0.945. This is a good spot to do another quick check. This is an exponential decay problem. K has to be negative. And it certainly, again, doesn't look negative just based off that. But no harm in going natural log 0.945 just to verify numerically, yes, we really have a negative value. We're thinking about properties of logarithms. Any input less than 1 is always going to give you a negative value. So we've got what k is. That's going to go right up here. But we still want lambda. Here's the half-life formula that was above example 3. Lambda is equal to negative natural log 2 divided by k. So that means in our problem, lambda is negative natural log 2 divided by natural log 0.945. And we just about have that. Go back to the calculator. Negative natural log 2 divided by natural log 0.945 gives us this figure here. What are we rounding to? 2 decimal places on this one. So we'll say that this is 12.25 years. And, well, we want to find the half-life, so we've got it, folks. Half-life of tritium-3. Not necessarily exactly that, but if this is what happened in the experiment, this would be our approximation for the half-life itself. We have to admit, when we're doing these kind of problems, there's variations in these experiments. Every time a half-life is given to you, it's truly an approximation. There's usually an actual confidence interval plausible values for that half-life. But we're trying to do the impossible task of giving the best approximation, and it's that value there. Just for the sake of curiosity, let's see if we can do one other thing with this. If you're doing this as a problem, say like on WebAssign, you could actually get a little bit more information and just directly ask Google, what is the half-life of tritium-3? Probably don't do the same question for plutonium 22, whatever it was, because that could put you on a list with the NSA. We have 12.43 years using Google from the output of one experiment. We have an estimate of 12.25 years, and you know what? We're in the right margin of error right here. That tells us our answer is very plausible. And even this right here, keep in mind, this is an approximation as well, but very likely a highly precise one. What tells us our answer is plausible? And now we have a half-life. If this much disintegrated, or this much remains is a better way to say it, after 1 year, then half of it's gone in about 12.25 years is what all this is saying. We have one more follow-up question to get through, but any questions or comments at the moment, folks? Okay, I felt like we should just ask one more part on this, so that's what part B is, just a little bit more extra practice. In part A, we're dealing with 94.5% is remaining after 1 year. So now the follow-up question is, how many years until just 20% of it remains? We have a half-life, so we can give a rough estimate, but we want to give as a precise estimate as possible using the model now. So here's how we're going to start off this problem. First, update by writing out mass at time t equals, still don't know the initial mass, m of 0, so we write in like that. Looks pretty funny, I know. That's e to the power of k times t. I'll put t in front, k after, so natural log 0.945 in place of k. Then once we have the model written in, we can directly attack this question here. How long would it take? We're talking about time. For 20% of the original amount, we're talking about the mass. So mass at time t being 0.20. When it says original amount, we're talking about mass at time 0 again. So this is the new equation that we would be solving. It is concerning with mass at time 0 on one end of this, but gets canceled out from the left-hand side. In place of m of t, we take the standard step of just doing this substitution, plug in m of 0 e to the power t, natural log 0.945, equals 0.20 mass at time 0. On this problem, let's take the bold step of just cancel right here. Mass at 0 appears on both sides of the equation. It's just an automatic cancellation. You don't have to show the division. Last thing is take the natural log of both sides. So natural log e to the power t times natural log 0.945 equals the natural log of 0.20. Another tremendous cancellation goes this way. And we're essentially done with the problem. Let me write out one more step so we can see it clearly. It's t times natural log 0.945 equals natural log 0.20. Last and final step here is to divide by that logarithm. So it's natural log 0.20 divide by natural log 0.945. I guess that wasn't the last and final step. It's said to round to 1 decimal place. So let's finish it out by doing the rounding on this one. So natural log 0.20 divided by natural log 0.945. This is the whole punchline to the problem, and it's about, I forgot the rounding, 1 decimal place, 28.5 years. And we did it, folks. Again, this is a really weird question, I have to admit to you. But I think there is a weird one just like this in WebAssign. So this is a good one to come back to see what do you do when there is no initial mass m of 0 provided whatsoever. That's what example 4 is really more about. And also just looking into the half-life equation again at the same time. But we did it, folks. This was our first really big application section of the course. Chapter 4 is going to have a couple more just like this one. But before we get into chapter 4 and all those extra applications, more about optimization, we still need a little bit more work on derivatives. Another role that section 3.6 plays is we're talking a lot about properties of logarithms to kind of help us out when now we're in section 3.7, actually dealing with them right away. Well, any questions at all, folks, before we close this section out and jump to the next? Let me make sure I saved it. I have a feeling I might save it like 5 times before I actually realize I've saved it or not, but let's now go on to section 3.7. Okay, here's how it starts. 2 interesting derivatives. Here's one and another. And then we'll just practice dealing with those derivatives. Actually, there's quite a lot going on these notes. When we go and calculate these derivatives, let's take a quick tour of these notes before we delve into them. Some of these derivatives are not going to go in the normal way. This is a normal chain rule right here. This one's a chain rule, but our goal in this section is to not use the chain rule on those kinds of problems. We're going to make a big deal out of every time we have the opportunity to use properties of logarithms, and this is an opportunity right here. No opportunity there, but we just talked about a cancellation of natural log with base c exponents. To use that property of logarithms right here, we take a problem which is a chain rule problem, and it's just taking the derivative of x. Same idea on this one. And we're going to drive that point really far home by differentiating this function t. It's kind of a nasty function, not something you'd want to differentiate by first principles. So we're going to do it in 2 parts. This is really the major idea of these notes. Do some challenging derivatives, and at the same time, let's bring out these notes, review properties of logarithms themselves. So if you open up this document, it tells you just about everything you might want to know about logarithms. It tells us first there's an exponential function. If we find its functional inverse, Then we get the logarithmic functions. But I think what most people are going to be looking into is this region right here, properties of logarithms. So let's take it with us. We take a slightly different screenshot. There's also a change of base formula, but I'm not really going to be too worried about that. It's more of these properties right here that are going to come up in our notes on our quizzes, our exams, and homework problems. So let's park that somewhere, how about right under here. Okay, so we're ready to get started. First things first, this is the derivative we like. The derivative of the natural logarithm of x is 1 over x, and that's a wonderful derivative. It's a fast one to calculate, but the only reason it works is because the natural logarithm of x is really a logarithm that goes like this. Natural log of x is log base e of x, and we know from doing the derivatives of the exponential functions, the logarithm to base b is extra special to have. Not only is the derivative of the natural log function really fast to say, same thing for the exponential function. So let's actually reorganize these notes in a slightly different way. Put in a vertical bar here, horizontal bar going this way, because the theorem we see here with the two formulas don't actually exist in isolation. There's two other formulas that go like this. D by dx of base b to the power of x, and d by dx of e to the x. So across the rows, these are really paired derivatives. When you think about the derivative of e to the x being e to the x itself, think of that as going along with derivative of natural log x is just 1 over x itself. So this is the new derivative on the left. This is the old one we've been working on. And now things get a little bit different here. It's all about what's going on with the base b. If the base b is e, then a slightly different property that we can say with logarithms is that, let me put it down here so that's not too big in the way. Natural logarithm of e is really just log base e of e. If we look at the properties of logarithms one more time, I forgot where I put them. Then the very first property, number 1, says, you take a logarithm to base b of b to the power of x, you just get x. The power here is really a 1, and so we just get a 1 through property number 1. So log base e is really special due to this property right here. And that's why when we differentiate e to the x, we just say e to the x. We don't put in natural log e because that's just multiplication by 1. No change really. But over here, we actually do. We must pay attention to the base. If it's b, and we don't know that b is e, if it's not equal to e, the derivative of the exponential becomes b to the power of x. This is a formula we used for the very first time in just 3.5, so it's a pretty new formula. And then we multiply by the natural log of b. So that's the adjustment from down here, going up to the general exponential function. And now same idea. If you differentiate the natural logarithm, it's just 1 over x. But if you differentiate a base b logarithm, it is 1 over x with an adjustment, multiplied by the natural log of b. So that's the adjustment right here. Let me try to make that look comparable. There we go. And this is the adjustment on the right with the natural log b. Strange kind of formulas altogether, but the major things we're paying attention to in these notes is this derivative, and we like that derivative a lot more when it comes up. It's the same thing, but no corrective factor, natural log b multiplied down the denominator. So that's the organization, and this is the great way to think about all 4 formulas at once. This formula goes with this one, and this formula here goes with this one as well. Next goal is just practice using these formulas. But any questions at all, folks, at the moment? Okay, starting out, we have 2 derivatives we want to do simultaneously. but that's because we want to compare and contrast what's happening to both at once. And as we look at that, we're also going to be paying attention to properties of logarithms. Actually, want to make that a little bit bigger. There we go. First, let's start off with f of x. That derivative there is not the easy one, but for both of these, there's a big problem with the form of the functions. It's using radical notation. We would much rather use exponential notation. So first step is just to fix both functions. Let's write an f of x as the natural log x. For taking the cube root, that just means it's to the power of 1/3. So exponents are more helpful for us in calculus, so that's our correction there. And now a g of x, this is natural log, but the cube rooting happens inside the function. It's a function composition just like the one over here, except this cube root is cube rooting the natural logarithm. That cube root is cube rooting x itself inside the natural logarithm. So I'll rewrite that as x to power 1/3. Now they're both ready to go. But now there's actually even a further adjustment. Looking into the g of x function right here, a property we're going to make loads of use of is property number 7. The major idea with property number 7 is that your power p, if you don't like where it is, you can trade it out and just make it go in front as a coefficient. That is massive in calculus. Because when you're analyzing this function, this is a chain rule problem. The inner function is a cube root. The outer function is the logarithm. But by property number 7, I'm going to write in properties of logarithms this way. And then you can come back to the table. I'm going to leave at the very bottom of the notes to see which property we're referring to. Property number 7 allows us to take that power 1/3, which is problematic. We express g of x as 1/3 times the natural log of x. This is now just the constant multiple rule. In fact, let's differentiate g right here. It's not a bad one to do. G prime of x. After we finished out the property of logarithm of moving the exponent in front, we'll just take the derivative of the natural log x. That's nothing but a 1/x. Constant multiple rule says because 1/3 is multiplying, you write that in first. Now we use the derivative for natural log x. That's a 1/x. We should simplify the function, but it's nothing major. We just get 1/3x. Now our work is totally done on that one. Let me see if I can move that table. There we go. And the interesting thing is we never ever had to use a chain rule at all in this problem. This is kind of the entire kind of theme of these notes right here. The more we ignore the properties of logarithms, the harder all these problems get. So they're really about these logarithmic properties when we can use them. But when we can't, like over here, that's where we have to realize that as well. We cannot use any property of logarithm if the power is affecting the natural log itself. Down here, the power has to be inside the input of the natural logarithm in order to use property 7. That means this one's a chain rule, and there's nothing we can do algebraically to get out of that. So let's analyze it as a chain rule problem. The inner function would be natural log x. I'll call this function 2. Let me control Z that mistake. Inner. The outer function is the cube root function. So we'll call that derivative 1. Outer. And here's what the process looks like on this one. F prime of x through the chain rule is first derivative of function 1 that we indicated. This is a power rule. 1/3 will come down. The new power is 1 less. So take your 1/3, visualize, subtract 3/3, and you get negative 2/3. But don't forget, it's also a chain rule problem. Let me just put it a quick border here. Because it's a chain rule problem, we have to multiply by the derivative of something. So this is what the analysis looks like each time on the chain rule. Then we grab that inner function, drop it into 2 spots, and step 1 is complete. this is our first time using a chain rule with the natural log involved, it feels different depending on how the natural log is involved. The natural log was the inner function. So this is the chain rule that we've used a lot in section 3.5. It probably feels like the pattern is more familiar. But here, the natural log is the outer function. We have to really be careful with this one in the chain rule because the pattern is now different. So we'll make a big deal out of that when we get to it. But first over here, all we have to do is finalize one last derivative. Again, natural log x is the nice one. This just gives you a fraction 1 over x, nothing further to do on it. So the end derivative, depending on how much you want to simplify, I'm going to just leave it in this form since I ran out of space. It's 1/3 natural log x to the power of negative 2/3 times 1 over x. Then our problem is completely satisfied. Well, these functions, depending on how you squint at them, they almost look the same, right? One small slight change in notation, the cube root is inside the natural log, means your derivatives are wildly different. This is kind of a theme in calculus as well. It's all about being very critical of how you write things down because the way these are being expressed is changing the meaning wildly on how the derivatives come into being. Well, that's example 1 down. We'll try it a few more before we call it a day, but any questions at the moment? Okay, on to the next. Now in example 2, these are kind of more routine homework problems like you're going to see in WebAssign. And even though we're making a really big deal out of properties of logarithms, another really big deal about them is we have to know when we can't use them at all. Just like in this f of x function, power 1/3 cannot move at all. It only moves here because it's inside the actual logarithm function. And same big problem with this one. We would love to break this down if we could, but all we have is 5, 6, and 7 for making this more broken down. There is no property for pluses and minuses whatsoever. And you know what? That's actually a theme. In algebra, we have a nice property that goes root a times b as the root of a times the root of b. It's a logarithm. We can say that log base b of a times b is log base b of a plus log base b of b. Weird choice, but let's let that one stand. That would simplify to a 1 in this problem. But if you try to do things like, say, square root of a plus b, you're stuck in the water. That is not root of a plus root of b. And the log of a plus b, same problem. And it doesn't matter if it's pluses. These could be minuses. It's not equal to, I should give this a base. Let's say base b. It's not equal to log base b of a plus log base b of b. Really, we want to emphasize not equal on these. So if you're copying these down in your notes, really scribble the not equal sign to make sure in your mind you know this is a non-formula we're saying right here. The theme in algebra is if you're strictly in an algebra problem, pluses and minuses are messing everything up right here. No properties to help. So this is a just direct compute the chain rule on this. No properties of logarithms can even help us out. Kind of weird, right? If they were being all multiplied, however, we would just use property 5 over and over again to expand it out as much as possible. So if we can't do anything to the format of this function, then that just means we have to analyze it as a chain rule problem. There's no getting out of it. The inner function this time is all of that. So that's derivative 2 we handle second. Inner. We also often color-coded the inner function as green, I believe. This is function 1, outer. And we color-coded that one as blue in the chain rule section. Now, as we go to do this chain rule, again, the format is wildly different. Pay attention to how this chain rule went at the same exact time so that we can spot that difference and be prepared when it comes up next. All right, so here's this one just as a really quick reference for us. With that one below mostly being ignored, let's start off this process above. The derivative of y we can write out as dy dx. I'll go with a good old y prime on this one. Now, first we handle derivative number one. That's the derivative of the natural logarithm, and we just discussed it, so let's put it down here for easy reference. It's only been on the notes for about 20 minutes or so. That's the formula for the derivative of natural log x. It takes the reciprocal of whatever your input is. So the format for this derivative is going to be 1 over something, using blue just to convey that's the derivative of the natural log, multiplied by the derivative of something else. This is the chain rule part where we always multiply by some other derivative. And now the function that's in her is the polynomial. So it goes into this spot and directly into this spot as well. So over here, 9x power 7 minus x power 6 plus 5x minus 11. And then again here, 9x power 7 minus x power 6 plus 5x. And I didn't give myself enough space, so let me put in just a little bit more, minus 11. So that's how this chain rule starts. And now let's compare this against, what did we do when it was in this format? When the natural log x was the inner function, that was the first derivative we took. So it came in here, and the natural log itself went inside. But now it's a totally different format. The way we wrote this out was informed by the new derivative, which just goes 1 over x. And so our new format goes, drop your inputs directly into the denominator, and then multiply by whatever that input was. So again, these are pretty confusing because in the section 3.5, essentially every single chain rule except for the exponentials looked about like this: a power coming down, one less, multiplied by a derivative. But now this thing coming down is the entire input to the function. So you don't want to pay too much, or you don't want to feel like this is the only pattern for the chain rule. The actual chain rule patterns come from here, the derivative you're taking yourself. So that's the takeaway on this one. I don't know why I deleted that. I should pause right here first. Any questions at all, folks, on the format where we're at right now? Okay, we're feeling pretty good about how this all got expressed in this way through that derivative over here. Then all we have to do is finalize the derivative. The first step is the hardest one, but the last step is just pretty much writing as fast as you can. Here's how it goes essentially each and every time. Denominator stays exactly as it was, 9x power 7 minus x power 6 plus 5x minus 11. And we're multiplying by something. That something we're multiplying could just be placed it directly into the numerator. So when I go to calculate this derivative, my output is just going to be rewritten right up top. So left to right, using the power rule, take 7 by 9 for a 63. X to the power 1 less, now power 6. Rinse and repeat, minus 6x power 5. On this term, we get plus 5. Now, this is the constant rule, not the constant multiple rule. It's the constant being added or subtracted. So that part goes to 0, and that's our whole derivative. So really what happened, what we did was, when we differentiate this function, we put that down below, directly copied. Then we put it over here, but we took the derivative with respect to x. That happens every time you do a derivative with the natural log as an outer function and a bunch of stuff inside, same exact pattern. But it's a new pattern, so that's why the step in the middle is a good one to just convince yourself that's the right steps to take. Well, that's our first one of the day, first big official one. Any questions at all, folks, on how this one gets computed? Okay, kind of a weird one, right? We didn't use a single property of logarithms, and we're trying to make a big deal out of them. But let's see what happens on the very next question. I'm pretty sure properties will come up. And yeah, this is one of those problems. part B. This is one of those questions where you can just hit this with a chain rule. You'll get the right answer. But the chain rule is tricky. This is a whole new pattern for the chain rule. If you can find your way to sneak out of it, it's well worth it. So this is properties of logarithms, property number one, really. But property number one is written for any base whatsoever. It makes it kind of confusing. Property number one says the natural logarithm of e is, let's write out this way, natural log of e to the x, that's more what we're looking at in our function right here, is just x. And I forgot to say what property number. This is property number one. Natural log e to the x is just x, deserves an exclamation. This is because the natural log of e to the x is log base e of e to the x. And that's what this is all saying. Log base b of b to the power of x causes a cancellation, giving you just x, is the idea with property number one. So back over here, if we use property number one, we just say f of x is x. And notice our work is done. F prime of x is then automatically 1. Weird question, right? We could have spent 3 or 4 minutes carefully talking about the chain rule on this one, doing all that initial analysis. But if we use properties of logarithms, that's it. We are done the moment we do the cancellation. And this cancellation going this way is the same exact cancellation we were looking at in section 3.6 when we're solving for k or solving for a time value. Well, that's another one down. Next one doesn't look as friendly, but it's good to have a little breather in the middle. Any questions at all so far, folks, with any one of these? Okay. Well, our new problem, it's getting nastier still. There's lots more going on inside the logarithm. The logarithm has a specific base 7, so we have to be careful with the derivative. But even more than that, we have a function of x multiplying another function of x, 15x times log base 7 of all of that. It's also fundamentally, and first and foremost, this is a product rule kind of a question. So we need to be really careful of both using properties of logarithms, using the product rule and the chain rule. So this would be a kind of a more challenging question when you see it come up in WebAssign. Let's start off with properties of logarithms. Inside here, I can't do much except correct that, write it in as an exponent of 1/3, then use property number 7. So let's write that in. Property number 7 will tell us that log base 7 of this thing, more helpful if we write it in as a 2x minus 8 to power 1/3. This becomes, the heart of property number 7 is working that exponent, 1/3 log base 7 2x minus 8. So the gist of property number 7 is we can make this a much better function by taking out one level of what's going to happen inside here. This is really a chain rule with 3 functions. There's the outermost, log base 7. There's the middle, the cube root. And then there's the innermost, the linear, 2x minus 8. That's a complicated chain rule. We've actually never done a chain rule with 3 levels of a function before. And that makes properties of logarithms a really great idea. We'll start by saying that h of x is 15x. This 3 that is right here becomes times 1/3, really what I'm looking at here, where we took the additional step of writing the cube root as a 1/3, times log base 7 of just 2x minus 8. We're now done with properties of logarithms, so we can tuck that away. And that also gives us another cancellation. H of x is now 5x times log base 7 of 2x minus 8. So first we use properties of logarithms. Now at this level, we need to use product rule. If there's a product rule, that means there's two functions of a variable x. This will be the first factor. This is the second factor. And so now we get to write h prime of x. We're now finally doing the derivative. A little bit of algebra before we even get there, but that's been a theme as well in section 3.3 and on. H prime of x is going to be, let me get my colors going. This structure. I made my second placeholders a little bit bigger because it's the longer to specify function. Don't forget to throw in your derivatives as in these spots here and copy in 5x. Here and here, we're treating this with a lot of respect as a product rule problem. We're going kind of slow and carefully because there's the extra noise of dealing with that logarithm and a chain rule all at once. Really, the strategy is be extremely methodical and you'll be highly accurate. So over here, log base 7, 2x minus 8, log base 7, 2x minus 8. So we've got it all filled in. Another thing that we need is just a recall. How does that derivative go? We only have looked at it for a few minutes and then we scrolled down. So here's the reminder on that one. Derivative with respect to x of the logarithm to base b of x is 1 over x times the natural log of b. So very similar derivative. We just have to be really aware that there's a base in the problem and tack it on once we differentiate the logarithm. So we're just about there. Derivative h prime of x will become, as we move left to the right, on this factor, it's just a 5. Copy log base 7, 2x minus 8. Copy the plus 5x. And then over here, let's pause, analyze this problem, and work it out through the chain rule. So two functions again. The inner function is 2x minus 8. You can spot that because it's really just a function composition. And this is a function going inside log base 7. So we do that derivative second and call it the inner one. And that means log base 7, that's the outer. So when we go to differentiate, here's what the pattern's going to look like on this one. First, the derivative of log base 7, put something in place of that x. We're just going to put a placeholder. Then we immediately multiply your placeholder by the natural logarithm of the base. So ln 7. 7 because we were dealing with the log base 7 itself. So that's the first factor. And then because it's a chain rule, we multiply by the derivative of something else. Here's the last factor that we essentially just shove back into the numerator once we calculate it. Inner function goes in both of those remaining positions. So both here and here. And now we just have to do that last derivative, put it all together. Any questions at this stage, folks? Where I should have said, at this step level, we're doing chain rule. Okay, let's put it all together. And our derivative, h prime of x is now going left to right. 5 log base 7 of 2x minus 8 plus. This 5x is going to go into the numerator. This is a derivative going to the numerator, but when we differentiate, we just get 2 from this function. So altogether, looks like we get a 10x up in the numerator. And 2x minus 8. Natural log 7 just directly copies in. If you really wanted to, you could actually simplify this. You can divide by 2 above and below. But if you left it in this format, no harm done. We went through the extreme stuff of dealing with properties of logarithms, product rule, chain rule, non-standard logarithmic derivative to get down to here. I think this is a lot of steps already. So if you ended up, or if you left your problem in this format, I would say that would be appropriate on this problem. But any questions at all, folks, on finalizing this one? Okay, didn't look like it was going to be really bad, but again, it's always a good idea with these kind of problems. Look before you leap, see what kind of properties of differentiation can come in, what properties of logarithms you can use. And sometimes these problems really go like this. You make a massive simplification, your derivative's immediate. Other times you have still a pretty hard derivative, but it would have been probably twice as hard if we didn't take those initial steps. So let's try this out all over again. Next problem is kind of nasty. We want to differentiate that function. This is a situation where let's actually leave properties of logarithms right in this spot. It's just going to stay here for the rest of the notes. Because if we don't use properties of logarithms, you can do this as a chain rule with 1, 2 functions, but then there's a quotient rule. And in that quotient rule, you have a 1, 2 more chain rules together with the product rule. I've actually asked this as a problem on a quiz, and people wrote it out to the best of their ability. Loads and loads of steps, something you would never even attempt to do in an exam setting, which is unfortunate because this is a very likely to be an exam 3 problem. Let's say that's right here just for extra emphasis. This will be similar to an exam 3 problem. It'll be in the same kind of format. There'll be a part A and then a part B. And even if you made a mistake in part A, wherever you differentiate, I'll look into how you're differentiating your last step and award partial credit based on that. So even if you made a mistake there, but I couldn't see any mistakes in your derivative, you'd still get full credit on part B. There's no double jeopardy to the problem. But we still have to do exactly what part A says and expand the function. Fully, that's probably the biggest word to emphasize, because if we don't use all the properties possible here, we're still dealing with a tough derivative. So let's make this part A our last problem of the day. I don't think I have enough time to do part B, but really part A is the major thrust of this whole problem. It's a review of properties of logarithms where, again, I complain a lot about pluses and minuses in algebra, but you know what? In calculus, multiplications and divisions are not things we want either. We would rather expand this as a whole bunch of pluses and minuses, because in calculus, we can just use the sum and difference rule over and over again, and it makes it easier. So if you're really fluent at this, you can do it in exactly one step. Just write down the answer. But if it's been a little while, if you're a little rusty, it might be a good idea to break this down slowly. The very first thing that is a problem is the division here. And so we're going to use property number 6, break up the division. That causes a difference in the numerator and denominator with a logarithm applied to both. So we'll write t of x is log base 5 of x cubed times, well, let's fix that exponent right there while we're at it. 7x minus 8 to the power 1/5 rather, minus log base 5 of x power 5 plus 3 to the 4th power. Now here, we could use true properties at once, but again, I want to really break this down slowly. We just used property number 6, and we're going to use all of those properties. So the next big one I would use is property number 5. We have a multiplication right here that we can use. So this is right here, property 5. We're going to invoke and say t of x equals log base 5 of x cubed. In property number 5, a product goes to a plus. And it's kind of nice in a way. Remember, the product rule in calculus involves a plus. Quotient rule in calculus involves a minus. So that's a kind of a nice way to organize these thoughts. So we'll split across plus and write in a new logarithm to the same base of 7x minus 8 to the 5th power. And although we could use a property here, let's just take one extra step and just copy. Minus log base 5, x power 5 plus 3 to the 4th power. So 2 properties down so far. I've split up the fraction, and then I've split up the multiplication. The last thing we'll do is correct all the exponents. So here, and here is property 7. Property 7 is nice. All it's saying is your exponents can now be regarded as coefficients. So writing in that last step, we've got t of x equals power 3 here comes down, and it's log base 5 of x. No chain rule at all in that problem left over. There's 3 functions here in the chain rule, making it really complicated. But if power 1/5 goes down, 1/5, I don't know why I'm calling it 1/5, times log base 5 of 7x minus 8, then there's still a chain rule, but this one's manageable, just 2 functions now. And same idea with this one. Move that 4 down. We now have minus 4, log base 5, x power 5 plus 3. Another chain rule here, but again, it's a manageable one. And what we'll do is go left to right, differentiating each term that we produced. So this is the way people would actually differentiate something like this. It's not a friendly function at all. But properties of logarithms take something that would take me personally, maybe 20, 25 minutes, because I'm going to make mistakes I have to correct in the middle. But if you expand this out, it's now a 2 or 3 minute problem, maybe 5 or 6 minutes if you're really careful explaining how the chain rule goes. Well, any questions at all, folks, with what is essentially a tour of properties of logarithms on this one? Okay, one thing I like about this problem is when you're taking or studying properties of logarithms in a college algebra class, they never say why you want to do this. Why do we want to fully expand things out with properties of logarithms? There's no explanation, and this is the explanation. In calculus, differentiation and integration works easier if things are spread out as much as possible with pluses or minuses, but this is the harder thing to handle with calculus. But this will be a good stopping point for us. If you like, you can take care of the derivative right away. But when we come back on Thursday, after addressing any review questions folks have on exam 2, we'll come right back here and carefully work out the derivative of what we have above. Well, this will be our stopping point for the day. Any last questions at all, folks, before we call the day officially? Okay, well, have a great afternoon, folks. Next Thursday, we'll just finish off this work here. After addressing any review questions you have on exam 2, I'll post the next notes for chapter 4 just in case we just run out of material. That's always a weird spot to be in. But have a great afternoon, folks. I'll see you all Thursday.